Okay, the second type of intermolecular force is dipole-dipole forces. These ones, in terms of strength, are in the middle. Yeah, they're stronger than London dispersions, but not as strong as the next one that we'll talk about. So these are dipole-dipole. Again, I'm going to go through by bullet. I think that dipole-dipole are the easiest to understand. They are found within polar molecules. So that's important for the first bullet there, that polar molecule part. And these are two examples there on the side. HBr is an example, and so is CH3F. Okay, again, these are polar molecules. HBr is polar because the two ends are very different. Okay, so they're not going to pull electrons equally. And then the other one is an example of a polar molecule because this end is different than this end. Okay, now, again, I think dipole-dipole are the easiest to understand because they're basically like magnets. So the way that these work is you have permanent dipoles. Now remember, dipoles are positive and negative ends. If you have polar molecules, you always have a positive end and you always have a negative end. It's not that temporary shift in electrons. Okay, it's always positive and always negative. So basically, these molecules just stick together like little magnets. So here's an example for that third bullet. Here is hydrochloric acid. Now, hydrochloric acid, chlorine is more electronegative than hydrogen. So that means that this chlorine end of HCl is always very negative, whereas the hydrogen end of HCl is always very positive. So when you have two HCl's very close together, they're held together by a dipole-dipole force, which is just where the positive end is attracted to the negative end. Now, if there was another HCl in here and it was attracted to one of those hydrogens, it would have to look like this. Okay, the chlorine would be attracted to the hydrogen because, again, the chlorine is very negative, whereas the hydrogen is very positive. And so you can draw that one in there. Again, hopefully that one's a pretty easy one to understand. The last one, which I think is definitely the most complicated, is called hydrogen bonding. And the worst part about it is that somebody named it hydrogen bonding. And it's not a bond at all. It's an IMF, or an attractive force. So again, it's just a terrible name, but we have to deal with it there. The types of molecules that undergo hydrogen bonding are polar molecules where there's a hydrogen covalently bonded to a nitrogen, oxygen, or fluorine. Okay, so the molecule still has to be polar, but somewhere within the molecule, a hydrogen has to be covalently bonded to a nitrogen, oxygen, or fluorine. Some of the most common examples we use for hydrogen bonding are H2O and NH3. Now, another thing that I want to show to you here is we talked about this with organics a little bit, but anything that has an OH group, which is called an alcohol group, that also experiences hydrogen bonding. And we'll talk about that more later this week. I just wanted to mention it today because it might show up in your work later. Okay, I want you to also write somewhere, oops, sorry, did it again. I want you to also write somewhere that hydrogen bonding is the strongest of the intermolecular forces. Okay, it's definitely the strongest one. Now let me show you why this works. It's a special type of dipole-dipole. So again, it's still a dipole-dipole because of the permanent dipoles, but it has that N, O, or F covalently bonded to a hydrogen because nitrogen, oxygen, and fluorine are so electronegative. What that means is they're so good at pulling electrons to itself. So just like HCl, chlorine is negative and hydrogen is positive, if this is an HF bond, the fluorine is so negative. It's like an extra strong magnet, which would make the hydrogen so positive. And they found that it was so much more negative and so much more positive that they had to give it its own type of intermolecular force, and that's where hydrogen bonding came into play. So for example, in each of these, the oxygen is so electronegative, so the electrons are so towards that oxygen that it makes the hydrogens extremely positive. And in NH3, that nitrogen is extremely negative, so it makes the hydrogens extremely positive. So it's still held together in the exact same way as a dipole-dipole. It's just an extra strong dipole-dipole. Okay, here is an example of hydrogen bonding between two molecules. Oops, sorry, went too far on me again. Okay, here are two water molecules, and here's how the hydrogen bonding works. Again, this oxygen is incredibly negative, this one's incredibly negative, and these hydrogens are both incredibly positive. So the hydrogen bonding, the attraction forms right here. We have a positive part attracted to the negative part. Okay, this positive part could be attracted to the negative part. And if I had another water molecule in there, maybe one that looked like this positive could be attracted to that negative, and this positive could be attracted to that negative. So again, it's just where the positives attract. And you don't need to draw all of those in. If you just draw in that first part of the example, that would be fine. And so those are your three types of intermolecular forces. Now what you're going to do now is you're going to get in those groups of 4. Okay, just turn your desk and pod off into those groups of 4. And you're going to work on a worksheet that you're about to get. Now what you're going to do is I'm going to do a first example for you. What the worksheet is going to give you is it's going to draw out a molecule like I've done here. Again, I'm just going to use water as an example. It's going to ask you whether it's polar or nonpolar. It's going to ask you the type of IMF, and it's going to ask you the strength of the IMF. Now, in terms of strength, we're going to use 1 as our weakest. So those would be our London dispersions. 3 as our strongest, which would be hydrogen bonding. So for water, I noticed that since there are lone pairs of electrons, this must be polar. If you forget whether a substance is polar or nonpolar, you can go through and look at that on your notes from yesterday. Since there is a hydrogen covalently bonded to an oxygen in there, this must be hydrogen bonding, which I know is the strongest, so it'd be strength 3. You're going to do that for every single molecule. I want you to you guys to have that worksheet done for tomorrow, and then you can start to work on your homework if you get that finished. Remember that you can do some of questions 1 through 7 now. So just take a look at the things that we've covered before. Hey, I will see you guys tomorrow, and I hope you guys have a good rest of the day.